Okay, hello folks, welcome back. So there's been a lot of questions about the homework. That's great. That means you're working on the homework. I'm just thrilled. Okay, so this thing's turned on now. Okay. Okay, all right. Okay, so the homework is so good and people are enjoying it so much, there's more homework. So assignment 3 is up. Okay, so assignment 3 is posted today, and that's due the following week. Okay, so not this week, but next week. Okay, so this is very good. If you're teching your solutions, that's amazing. The LaTeX is also available here. Okay, so if you want the LaTeX code for the assignments, it's there. Okay, very good. I just want to point out another thing that we were talking about at the beginning of the course, which is this sort of way of keeping track of how the course is going. Let's send. Go. Oh, go. Right, okay. It is really, really incredibly bright. Does that help? I'm not sure. Okay, so, oh. Okay, now it's too bright again. So I highly recommend filling out this thing. So this is in the syllabus. It's on page 6 of the syllabus, I think. This is sort of a score sheet for the course. I highly recommend filling it out. As you can see, I've been trying to follow along with the homework. So when I do questions, I circle them. Okay, some of them are a little bit harder and I get frustrated. As you can see, I've been showing up to office hours. It's very good for the professor. And I'm putting in a little bit of time in the course. Okay, so I put in 21.5 hours in the first week. I expect you guys to put in about 10. Okay, so I really, really recommend trying to keep track of this as you go through the course, okay? So if you haven't started, now's a great time. Okay, so there's that. Very good. See? Okay, good. Okay. So I'm going to leave the projector up because I want to project some examples later. Okay, so what are we up to this week? Okay, this week we've sort of got 2 major topics. Okay, we've got differentiation. And the chain rule. Okay, so we've got, these are sort of topics we had in first year calculus, but we're going to kind of go farther with these topics. So in last week, we had the following definition, right? So we had the definition of a partial derivative, right? So where we take a function and we take its derivative in one coordinate. So take a moment and try and write down the formula that we used to define that thing. Okay, try and recall from last week how we take the derivative in one coordinate. Okay. There's multiple different ways of writing it down, so try and write something down and see if we write the same thing. Yeah. Okay, so one of the ways of writing this thing down is as this limit of h. Okay, so what we do is we take our input, we add h copies of a basis vector, and then we take the rate of change. So this measures the rate of change in the direction EI at the point x. Okay, very good. So that's what the partial derivatives are. So these are the partial derivatives. Right, so if we've got a function of n inputs, then we're going to get n partial derivatives. Okay, but I want to point out that we need to be sort of careful with this definition because it's more subtle than it looks. Okay, so let's see what happens if we take the partial derivatives of this guy at the origin. Okay, so what do we get as the partial derivatives there? So this will be the limit. Oh, yeah, sure. Yeah. Sorry, come again? A lot louder, sorry. Okay. Okay, good. Oh, right. Is it this thing? Sorry. Is it that this looks like a 2? Is this the thing? Right. This is a 2, the letter D. 2, the letter D. Okay, good. So let's take this partial derivative and see what we get. So this is f of x, or sorry, 0 plus h, 0. Over h. Okay, so when we take the partial derivative in the x direction, we're adding on a plus h to the x coordinate. We take the derivative of that. But notice when we plug in 0, 0, we're going to get cubed root 0 plus h times 0 minus cubed root 0 times 0 over h. When we plug in the variables, there's a lot of zeros happening. Okay, so for every value of h, this thing's equal to 0, so the whole thing limits to 0. Okay, in exactly the same way, okay, we get that the derivative at y will also be 0. Okay, so what this means is that there's no change in either of those directions. Okay, but I want to show you what this thing looks like when we graph it. Okay, when we graph it, we see something very strange happen. Yeah, okay, that's all live. Okay, so let's graph what this thing looks like. Oh no, good. Ooh, fancy computer graphics in class. Ooh. Okay, I'm impressed. So, what do the tangent vectors look like there? We notice that in some directions, they're very big. Along the x and y axis, though, there's this fold. Right? If we look along an x-axis, we see that there's no change. Right? There's no change along the axes. Okay, now I want to investigate what happens when we go along the line y equals x. Okay, when we go like this. So when we go along y equals x. Okay, so let's see what happens then. Okay, so I want to find a different direction of approach to that point there. Okay. So to answer that question, we're going to plug in h and h. Okay, so we get the limit as h goes to 0. All over h. So we get this guy. Okay, so on the top, we have h to the 2/3. On the bottom, we have h. When we cancel, we get this. Okay, so this limit here does not exist. Okay, so that explains why we have this weird behavior. Along the x-axis, we have 0. Along the y-axis, we have 0. And then there, at along y equals x, we have this fold. We have this cusp. Okay, so this means that we've got sort of a bad derivative in one direction. Okay. So I want to give a name to this process of looking at derivatives in one particular direction. Okay, so the partial derivatives are along the axes. Let's give a name to the thing we just calculated up here. The directional derivative is the following fellow. Okay, so we do df dv. We get the following thing. Okay, so this measures the rate of change in the direction of v. Oh, is everything okay there? Is everything all right? Cool. Okay, so this is rate of change in direction v. Okay, so we can say that this guy is the rate of change in the direction 1, 1. Okay, very good. Okay. Okay, so we want to find a particular directional derivative. So for this function, and v is 1, negative 1. Okay, so what's this measuring? This measures the rate of change of our function, or how fast our function is changing at this point in this direction. Okay, so we write out the definition. Okay, so we take that direction vector, we scale it by h, we add it to the point we care about, and we take this limit. Okay, so let's do the algebra and see what we get. Okay, so when we do the vector algebra in here, we get this. Now, when we apply the definition of our function, we get a phone call, apparently. Okay, so we use our definition of our function. This 5 comes from plugging 1, 2 into x squared plus y squared. Okay. All right. Now all the constants cancel off. We get do the algebra, we get this. We take the limit. And we get -2. Okay, so at that point and in that direction, our function is decreasing. Okay, we're going down. Okay, so that's what a directional derivative is. So from the example that we've got projected up, we can see that directional derivatives don't always exist. Sometimes they do exist, sometimes they don't exist. Okay, so now we come to the topic of differentiability. Oh, are there questions or thoughts? Yes, good catch. Right, yeah, so I start with 2h squared, I cancel 1h, the 2 should remain, but I take h to 0. Okay. Any other questions or thoughts before we move on? Yes?
Does the length of the directions vector matter?
Good question. It turns out no, which is kind of subtle. I guess the reason why it won't matter too much is because we wind up scaling by h anyway, right? Like we divide out by h. Okay, so good question. Subtle, but good question. Wait. Yeah. I'll think about that more. That's a good question. Okay. So now we get to the topic of differentiability. Okay. So so in our one variable course, we have the following example. So okay, the function y equals absolute value of x does not have a derivative at the point x equals 0. Okay, so this is sort of a subtle thing about this function. Oh. Right, if we graph the function, we get the following behavior. We have the tangent line has slope -1 for a long time. Then suddenly it switches to having slope 1. Right? And at this point, x equals 0, we don't really have a well-defined tangent line anymore. Okay, so we say that this function doesn't have a derivative at that point because there's no tangent line there. Okay? Things get a lot more subtle in 3 dimensions though. And I want to graph a couple examples of what can go wrong in several dimensions. Okay. So in several dimensions, we can fail to have a derivative for different reasons. Oh, geez. Oh, no. Okay, so here we've got a graph of a cone. I guess that this is the very high-tech way of doing this with a piece of paper. Ta-da, it's a cone. But we can graph things on computers, and that's amazing. So here we fail to have a derivative at 0, kind of for the same reason. If we try and put a tangent plane at that cone point, then there's going to be no tangent plane, right? We could put many, many different planes that all go through that same point. So that's one thing that can happen in several variables. That's a lot like, oh geez. That's a lot like what happens in one variable. Okay? We can also have other things where we sort of have some kind of singularity. So here we'd get, right, so here we don't have a tangent line or a tangent plane at any point on that circle. Okay, the circle x squared plus y squared is 1. Everywhere on that circle, we'd fail to have a tangent plane. All right, because we have this sort of singular behavior there. Okay. Another thing that can happen, and this graphing calculator doesn't do this. Here, let's switch to a different graphing calculator. Is we can have things like this. Plot. Let go. I think we could beat the computer at this rate. Okay. Well, we'll wait for that to load. What it's supposed to look like is a fold. Okay? If we have a fold in the graph of our function, then we'll fail to have a tangent plane at any of the points along the fold. Okay? So to summarize, we can have cones. Right? So things that look like this. So that would be a graph like this. We'll have a cone at the origin. We could have a fold. Okay. Or we could have a singularity. Okay, so there's several reasons why we can fail to have a derivative in multiple variables. Okay, now I'd like to define what it means for something to be differentiable. Okay, so we've seen that there's more issues than in one dimension. Okay, we say that something is differentiable at a point if there's a tangent plane to our function at that point. Okay, so what does that mean, having a tangent plane? Okay, so we'll say that something has a tangent plane if there's a normal vector n such that the following limit holds. That as x goes to p, we get the following limit. Okay. Okay, so what's this limit saying? It's saying that our function gets very close to this plane here. Okay. So I'd like to do an example of finding one of these tangent planes, showing that something is differentiable. Okay, so we want to show that this guy is differentiable at this particular point. Okay, so we need to find a vector n which does this. Okay, we plug in our points here. So 3 plus 4 is 11. Sorry. 3 plus 8 is 11. Minus. Okay, so writing out exactly what we need, we get a statement like this. Okay, very good. Okay, so now we're in this position where we need to find this vector n. Okay, we want our vector to be sort of similar to our function somehow. The tangent plane should have the same slope as the function. Okay. Right, it should in every direction have a similar slope. So we'll try this out for our derivative. Okay, so let's see what that gives us for our limit. Right, following this idea of similar slope. We get this. So now we've got a whole bunch of explicit numbers to work with. Okay. So the x's cancel, right? We get okay, and now note that everything in the denominator cancels off. The x's cancel, the y's cancel, the 11's cancel. Okay, so we found a choice for our tangent plane that made the limit we needed go to 0. Okay, I want to spell out exactly what that choice is because it'll come up over and over again. Yes, sure.
Put the magnitude 0 over some vector that's going to 0.
Yeah.
Isn't that an indeterminate form?
Ah, right. Yes. So this is a question probably a lot of people have been wondering about. Very good question. So there's a distinction based on where the chalk brushes are. I guess they all live over here. Right? So there's a distinction between the following two kinds of phenomena. And I think it's very important to be precise about it. Okay, so here we've got an instance where every number that we're plugging in, every value of x, we know that it's 0 divided by that number. So it's 0 divided by 1, 0 divided by a half, 0 divided by a third. Every time it outputs 0. So the limit goes to 0, no questions asked. Right? Here we get, if we plug in directly, we get sine 0 over 0. And now we have an indeterminate form, right? So this is indeterminate. Okay. And if we remember our first year calculus stuff, it turns out that this limits to 1. Okay? So in this limit, our function is constantly 0. And in this one, our function's changing. Okay, so in this case here, in this case here, we've got 0 divided by something. So we're constantly outputting 0. Okay, so we're in this case. Okay, so I want to spell, oh, yeah, sure.
Isn't there a typo between x and y approaching 1, 2?
We erased the exact statement of the question. Sorry. At y equals 3, 4. Okay, so x and y should be approaching this point.
But in the earlier, we had x and y are approaching 1, 2, towards the
Oh, so yes, sorry, so this is a typo then. Sorry, it should be consistently 3, 4. It should be going to 3, 4 everywhere. Okay, there's one last point I want to make. I want to just introduce a bit of notation. Okay. So in this example, we chose our normal vector to have the same slopes as our function. Yeah, so we said our normal vector will have the same derivatives as our function. This is generally true. Yeah? Yeah, it doesn't necessarily mean it's in 3 dimensions. This could be in Rn. Okay. This vector is so important that we give it a special name. Okay? We call this vector the gradient of f. Okay, we call this vector the gradient of f because it's so helpful in doing calculations, and we give it the following name as well. Okay, so we put this upside down triangle for the gradient of f. Okay, very key vector that'll keep coming up in our course. Okay. So that's what I want to end off with today. We've covered a fair bit about differentiation. Next lecture, we'll cover the chain rule in more depth.